When you think about calculus, you probably picture these smooth, predictable curves, right? But what about the real world? It's full of things that are constantly switching on and off. Well, today, we're going to dive into the one mathematical tool that acts like calculus's very own on-off switch. It lets us model everything from a simple light switch to a sudden, powerful force.
So here's our game plan. We'll kick things off by talking about the problem of these sudden changes. Then, I'll introduce you to the brilliant function that was designed to solve it. We'll see how to use that function to control other functions, walk through a few really important examples, and at the end, we'll tie it all together to see why this is so critical in fields like engineering and physics.
Think about the kinds of functions you usually see in a calculus class. Sine waves, parabolas, all very smooth and continuous. But reality? It's not always so smooth. It's packed with sudden events. A circuit powers on. A force gets applied instantly. A digital signal jumps from low to high.
And that leads us to the fundamental question, right? How do we bridge that gap? How can our mathematical toolkit, which is so good at describing gradual change, possibly handle something as basic and instantaneous as flipping a switch? It feels like a total paradox. But, as it turns out, there's a surprisingly elegant solution.
And that solution is the absolute hero of our story today, the Heaviside step function. It is a beautifully simple, wonderfully powerful function designed for literally one purpose, to act as a mathematical on switch.
The real beauty of this function is just how simple it is. We call it u sub c of t, and it's defined as 0, just 0, for all time before some specific moment c. Then, bam, right at that moment c, it jumps up to a value of 1 and just stays there forever. It is the purest mathematical way of saying something was off and then it switched on.
Of course, when we're trying to solve differential equations, the real power comes from its Laplace transform. And the transform of our little switch here is this exponential term, e to the minus cs all over s. This is one of those foundational formulas you just have to know. It's the key that unlocks our ability to use this on-off switch to solve much, much bigger problems.
But a simple on-off switch is really just the beginning. The real magic happens when we use this switch to control other functions, to turn them on or off whenever we want. And to do that, we need a special rule. It's called the second translation theorem, and it builds directly on what we just learned.
Now, this theorem comes in two essential forms, and knowing which one to use is everything. Think of them as two different tools in your toolbox. Form 1, the inverse-friendly one, that's your go-to when you're working backward. When you see that e to the minus cs term in a problem, this form tells you exactly how to get back to the time domain. Form 2 is for going forward, when you start with a function of time that gets switched on and you need to find its transform.
Okay, enough theory. The best way to really get a feel for these theorems is to just see them in action. So let's walk through 3 examples, step by step, to really nail down how this all works in practice.
First up, let's model a pulse. Imagine a constant force of 3 is suddenly applied at time t equals 2, and then, just as suddenly, it's turned off at t equals 5, so it's on for a very specific window of time. How in the world do we write that mathematically and then find its transform?
The solution here is actually pretty clever. First, we turn the function on at t equals 2 using 3 times u sub 2 of t. Then, to turn it off at t equals 5, we just subtract another step function, 3 times u sub 5 of t. It's brilliant! We just transform each piece separately using that basic formula we saw, combine them, and there's our final answer. It's just like using one switch to turn the lights on and a second one to turn them back off.
Okay, quick heads up. This next example uses Form 2 of our theorem, and there is one specific step where students trip up all the time. So let's pay really close attention to the details on this one.
So here's the problem. We have a standard sine wave, but it doesn't start right away. It's just 0, 0, 0, and then at time t equals pi, the sine wave suddenly kicks in. This is a classic textbook application for that forward-friendly Form 2. All right, let's walk through this carefully. Step 1 is just identifying our parts. C is pi, and our function g of t is sine of t. Easy enough. Now, step 2, this is where the trap lies. The formula requires the transform of g of t plus pi, not just g of t. So we have to figure out what sine of t plus pi is. A quick trig identity tells us that's actually equal to negative sine of t. Forgetting to do that shift is the #1 mistake people make. Once we have that, the rest is easy. We transform negative sine of t and multiply by our exponential term. Done.
So we've gone from the time domain to the S domain pretty successfully. But a lot of the time, when we're solving differential equations, we need to do the exact opposite. We'll end up with a transform, and we have to figure out what function of time it came from.
So for our final example, let's tackle that. We are given the Laplace transform f of s equals e to the minus 2s, all divided by s squared. Our job is to work backwards and find the original function of time, f of t.
I like to think of this as a bit of detective work. That e to the minus 2s term is our biggest clue. It immediately tells us two things. We're dealing with a step function that turns on at c equals 2, and the rest of the function is shifted by 2. So what we do is we ignore the exponential for just a second and find the inverse of the base function, 1 over s squared, which is just t. Then we apply our rule from form 1. The answer is the step function, u sub 2 of t, multiplied by our base function shifted in time, so f of t minus 2, which is just t minus 2. And what this describes is a ramp function that's 0 until t equals 2, and then it starts growing in a straight line.
So we've seen the definitions, we've walked through the theorems, we've done the examples, but let's zoom out. What's the big picture here? Why is this such a fundamental tool in math and engineering?
Well, it really all boils down to this. The unit step function is our mathematical switch. It lets us take these messy, piecewise functions and write them as one single clean expression. The second translation theorem is the engine that actually lets us work with those expressions using Laplace transforms. And the result of that is huge. We can now accurately model and solve problems that involve real-world systems with sudden changes, from the voltage in a circuit to the sudden impact of a force on a bridge.
And that leaves us with a final thought. Now that you've got this tool in your arsenal, just think about your own field, or even just the world around you. Maybe it's a thermostat kicking on, a drug being administered at a very specific time, or a financial model where a policy suddenly changes. What on-off systems could you now describe and analyze with the power of calculus?